Alright, well, we're moving on to chapter 3.1, the definition and examples of rings. Now before chapters 1 and 2, we've been working on just a particular type of numbering system, which is the integers. Now we're going to kind of broaden our base a little bit and talk about more general sets of numbers called rings. So a ring is a non-empty set equipped with two operations, usually written as addition plus and multiplication times, satisfying the following conditions for all A, B, and C elements of R. And this notation with the little e in there, elements of R, is going to be a symbol that you are allowed to use for, instead of writing the word elements of R, you can write the little ER. As we get on more chapters, we're going to start allowing more and more little symbolisms, but still the concept of divides, you cannot write the little slash mark. This is a writing intensive course. So a ring is a non-empty set R of elements consisting with two operations, an addition and a multiplication, however those are defined, that satisfy the following conditions for all A, B, and C's elements of R. So, number one, if A is an element of R and B is an element of R, then A plus B is an element of R. That is called the closure property under addition. A plus parentheses B plus C is equal to parentheses A plus B close parentheses plus C. We move the parentheses around under the addition. That's called associativity under addition. A plus B is equal to B plus A. We move elements around. That's called commutativity under addition. There exists a zero element, and I put the zero with a little subscript R on there because you don't know what the elements actually look like. But there's a zero element relative to whatever ring we're talking about, R. The element of R such that when I take 0 in R, add it to A, that's the same thing as A plus 0 in R, which is the same thing, it equals A for every A in R. That is called the additive identity, the zero element. So, but the zero element may look a little different. Like, for example, in matrices, you got rows and columns of zeros. In complex numbers, it's 0 plus 0i. So that zero element can look a little different. So I put the little notation on there, 0 with a subscript R. The next one. For each element A in R, the equation A plus x equals 0 has a solution in R. Now I know what you're thinking. Well, why don't you just solve for x and subtract a from both sides? Well, yes, that's exactly what we're doing, but I'm not sure what that subtraction, which hasn't been defined, or the negative element has not been defined, so we define it this way. The solution to the equation a plus x equals 0 will also be inside of R. You're right, it is quote-unquote the negative a, but we don't know about negatives yet. Those have not been defined. That is called the additive inverse property. Number 6. So the first 5 properties deal with addition. Now number 6 is this. If A is an element of R and B is an element of R, then A times B is an element of R. That is your closure property under the multiplication. A times B times C is equal to A times B times C. You can move parentheses around with the multiplication. That's called associativity under multiplication. And then property number 8 is this. A times parentheses B plus C is equal to A times B plus A times C. And you can put the dots in there and typically put two elements beside each other, also divine multiplication. But A times B plus C is equal to A times B plus A times C, and B plus C times A is equal to B times A plus C times A. You can distribute in the front or you can distribute in the back. See, I didn't say these guys are equal to each other because I don't know if A times B is equal to B times A. Under addition, that's true, but under multiplication, that may not be true. So you have to worry about your distributive property, through distributing in the front and distributing in the back. But if you have all 8 properties here, properties 1 through 8, with a set R that is has a defined addition and a defined multiplication, properties 1 through 8 by definition form what we call a ring. This is a ring. Now, this is chapter 3.1. So introducing a chapter 3 with new material, you're going to have lots of definitions. So again, we have a lot of definitional terms on the right hand side. These 8 properties, if you satisfy those, you have what we call a ring. And then from a ring, we move on to different types of rings. So if we continue on, we have more definitions. Given R is a ring, and for all A and B elements of R, we have A times B equals B times A, then R is a commutative ring. First off, you got to have a ring. So you got all your 8 properties. And then if you have the property A times B equals B times A for all A and B and R, then you have something called a commutative ring. So I call that property number 9, but that's actually a definition, commutative ring. Property number 10 is also a definition. Given R is a ring, and if there exists a 1 element inside of R, 1 subscript R element of R, such that for all A in R we have A times 1 in R equals 1 actually in R times A, which is equal to A, then R is a ring with identity. That little 1 element that we're talking about here is actually the identity. It's the 1. When you multiply 1 by anybody, you get anybody back again. But again, we have to put the little subscript R on it because I'm not sure what elements in R look like. For example, if it was a matrix, then it would be a square matrix, and the identity, that 1 element, is 1's the diagonal and 0's off the diagonal. So you got your square matrix, which would be the identity in matrices. But that's a ring with identity. So 1's look a little particular. Like, for example, in complex numbers, 1 plus 0i would be the identity element and stuff. So there's lots of different ways the 1, the identity element, can look. So we denote that by 1 with a subscript R on it. And so you do not have to be a commutative ring to have a ring with identity. A ring with identity does not have to be a commutative ring. But if you happen to have both properties, 9 and 10, or we're in math people, so don't think too deep in this one. And if R is a ring that is both a commutative ring and a ring with identity, then we call R a commutative ring with identity. So if you actually have both properties, 9 and 10, we just put them together and call it a commutative ring with identity. But then we get a little bit stronger. Property number 11, again, is a definition. An integral domain is a commutative ring with identity that has one more property. That satisfies the property that whenever A and B are elements of R, and we have A times B equals R, then either A, the first guy, had to be R, 0 in R, or B, the second guy, had to be 0 in R. So it's the idea of when I multiply 2 elements together, get 0, either the first guy is 0 or the second guy is 0. Remember, way back when, this is modern abstract algebra, we got lots of definition stuff. We had a definition called a zero divisor. A zero divisor is a non-zero element, A, that when you multiply it by another non-zero element, B, the product is 0. That's when you have zero divisors. So in English, an integral domain is a commutative ring with identity, so it satisfies both properties 9 and 10, commutative ring with identity, and it doesn't have zero divisors. So if I ever have a product equal to 0, either the first element was 0 or the second element was 0. And then the last definition is pretty much when you have all your properties. There's one more property, and that is a field. A field is an integral domain, so you're kind of adding on to this statement up here, with the property that for any non-zero element, A not equal to 0 in R, element of R, the equation AX equals 1 in R has a solution in R. Now, what you would call this AX equals 1, officially in high school algebra here, you would divide by A on both sides. Remember, division is not really allowed here, but it's basically called the multiplicative inverse. What you multiply by A to actually get back to 1. And every non-zero element A has a multiplicative inverse. When you have an integral domain where every non-zero element has a multiplicative inverse, that's actually called a field. So we're kind of building on these definitions. Commutative ring, ring with identity. Commutative ring with identity, integral domain, and a field. So you've got lots of different types of rings out there. You start out with your basic ring. Then you go to the famous commutative ring. And then from the commutative ring, you could have a different kind of ring called a ring with identity. If they have both of these two properties, then you have a commutative ring with identity. And then if you have the property that you don't have zero divisors, anytime two elements A and B and R, that the product A times B equals 0, then either the first guy is equal to 0 or the second guy is equal to 0. That's called an integral domain. And then if you've got an integral domain where every element that's non-zero in R, the equation AX equals 1 in R has a solution. The multiplicative inverse of every element, non-zero element is in R. That's called a field. So there's different levels and kinds of rings. So I tried to draw you a picture off this thing, so make my picture look a little bit better here. So here's the idea of how things fit together. This is the universe of rings. Now inside this ring you have commutative rings, and outside this ring you've got non-commutative rings. A non-commutative ring is where the A times B is not equal to B times A. And we'll talk about those kind of examples in a second. You also have the world of rings with identity. You either have a ring with identity or you don't have a ring with identity. So you're either inside this little circle or you're outside this little circle. The section where they intersect, you have a commutative ring and a ring with identity. This world right here is a commutative ring with identity, so you have both properties. And inside of that, you have a smaller set called an integral domain, and inside of that you add one more property, makes it even smaller, you have fields. So this is kind of a picture of how the diagram of how rings put together and where to kind of ring and where it's actually going to be located at and stuff. So let's talk about some examples. Now, of course, we've been just finished up chapters 1 and 2 where we were playing with the wonderful world of integers here. And when it comes to integers, an integer is an integral domain. It has all the 8 properties of a ring. It has an addition, multiplication, where everything's defined. It commutes. A times B equals B times A when it comes to integers, for any A and B an integer. It has an identity, which is 1 is in there. 1 times anybody is anybody, so it's a commutative ring with identity. And it also has the property that when I multiply two things together and get 0, either the first guy had to be 0 or the second guy happens to be 0. That the integers is an integral domain. However, if I do z mod n, playing that wonderful world of z mod n, where n is not prime, then we actually get those zero divisors. So we won't be an integral domain. It still commutes. There's an identity. The 20 bracket 1 is the identity element here. But because I can, for example, Z6, equivalence class 2 times equivalence class 3 is equal to equivalence class 0, but 2 and 3 are not 0, this does have zero divisors, which means it's not an integral domain. It will make it just a commutative ring with identity. Now we'll go back, and this is why linear algebra is a prerequisite to the class. So when I need some really weird examples, go to the matrices. So, but to be able to focus on multiplication and addition, you can only have square matrices. It's got to be n by n square matrices. So we call that m sub n. That's the size of n by n because they got to be square matrices. So you can add them and multiply them. But you'll notice that we know in matrices, matrix A times matrix B is not necessarily equal to matrix B times matrix A. So it does not commute. So it's a non-commutative ring. But it does have an identity. You know, the square matrix with 1 on the bang diagonal, 0 is off diagonal. So this is a ring with identity, but it does not commute. Now, something that you'll be quite familiar with that has all the properties are rings, complex numbers, and Z mod P. Now, if you think about integers back up here, the reason why it's not a field is if you look at any arbitrary element, like, for example, 3. 3 is an integer. The multiplicative inverse, what do you need to multiply 3 by to actually get back to 1? The identity, multiplicative identity, is 1/3, but 1/3 is not an integer. That's why it's not a field, it's just integral domain. But these guys, the non-zero elements are also, their inverses are going to be each one of these sets. And this real numbers, complex numbers. Here's another one, the double back Q. This stands for rationals. Rational numbers, you know, fractions. Real numbers, throw in your irrational numbers like pi and e and square roots of 2 and stuff. Complex numbers are typically defined as a plus bi, where a and b come from the real numbers. I represents that square root of -1. Imagine if you could do that, complex numbers. And the new thing that we just discovered, Z mod P, where P is prime, Z mod of prime. All of these guys are going to be fields. Each one of these guys is a field. All right, so let's look at some other ones. And so here's one I threw down for you guys. I called it, there's no direct symbolism for this guy, it's called 2Z. Z stands for integers. So 2 times the integers is the even integers. Even integers, they commute. Even plus even is even times even is even. You got the closure property, they got associativity, all the things. It actually commutes because it doesn't matter what order you put the even integers in, but it doesn't have an identity. The identity in the integers is 1, but 1 is odd, it's not even. So it's a commutative ring, but it does not have an identity. So we just say even integers is a commutative ring. Now the integers themselves is an integral domain, but inside that you have the even integers, and that forms a ring on its own, and that is called a commutative ring because it does not have an identity. So you look at these things, well, I've done all kinds of those kind of numbering systems before. So are there any other numbering systems out there that we can actually start focusing on? Well, yeah, they don't actually be numbering systems, but they're elements that are grouped together. So let's talk about this guy here. The set of continuous functions on the real. So we're talking about functions themselves. Now, and when it comes to functions, on the real numbers, so your domain is all real numbers. I'm going to call that little pointy bracket C for continuous functions here, just to give myself a name. It's the C set for continuous functions here. So f of x and g of x are going to be continuous functions. See, f of x and g of x are elements of this C. If f of x and g of x are continuous functions on all real numbers, that all real numbers will have to be their domain. So they're defined everywhere. This is actually going to form a ring because think about it. You can add continuous functions, you can multiply continuous functions. So, being that when you add, you've got all the properties. When you multiply, you can, you got closure and multiplication. You got associativity under addition and multiplication. You got commutativity under addition. You actually have commutativity under multiplication. It doesn't matter what order you take f of x when you multiply it by g of x. That'll be the same thing as g of x times f of x, because the coefficients also for these guys are coming from the real numbers. The domain is the real numbers, and the coefficients can be real numbers, so order does not matter with this stuff. So what kind of rings is it going to be? Well, a lot of people think it's going to be a field. Well, let's see here. Could it possibly be a field? Let's see. Let's pick it up here. It's going to be a commutative ring. It is a ring. It's got all eight properties. It commutes because f of x times g of x is the same thing as g of x times f of x. So it's a commutative ring. Does it have an identity? Sure. So let's write that down. The identity would be the function, I'll call it e of x just to give them a different letter, is equal to 1. And wherever the coefficients come from, we're coming from the real number. So this is the real number 1 there. It's a continuous function. I can even graph it for you. Let me show you what f of e of x looks like, equal to 1 looks like. It's 1 and it's a horizontal line. But it's clearly a continuous function. And you multiply 1 times any other function, you get any other function back again. So it's a commutative ring with identity. So we're up to ring, commutative ring, ring with identity, so now we're a commutative ring with identity. Is it an integral domain? So, and I'll abbreviate that, int domain, that means integral domain. So is it that? Well, let's see here. When I ask for that, what I'm really asking for is if you got two arbitrary continuous functions, f of x, you multiply it by g of x, and it's equal to the 0, the real number 0, if it's equal to 0, then is it true that either f of x equals 0 or g of x equals 0? And that's basically the question. Because if it is, you've got an integral domain. If it's no, you don't. And so a lot of people argue with me, and of course they say, yeah, if I got two functions that set flat out equal to 0, that meant that either the first guy had to be 0 or the second guy had to be 0. And you're wrong. It's not an integral domain. I said it had to be a continuous function. I didn't say it had to look nice. So the trick to show this one, and I'll call it a trick, is don't forget piecewise functions. As long as the pieces connect, piecewise functions can be a continuous function. So if I sit there and pick out, piecewise function, here we go. I'm going to let f of x be equal to piecewise function 0 if x is less than or equal to 0, and let's say x if x is strictly greater than 0. This is a piecewise function, and it's continuous because I can graph this thing. Anything less than 0 is going to be 0, so you flat line it to the left, and you get x, which makes y equals x is a 45-degree angle for any x greater than 0. And it connects right there, so it is continuous. Now watch this one. I'm going to let g of x be equal to, just to be different here, I'm going to let it be equal to x squared if x is less than or equal to 0, so your domains are going to match up here. So g of x equals x squared if x is less than or equal to 0, and 0 if x is strictly greater than 0. So what that's going to look like over here is if you got a negative number less than or equal to 0, you square it. So negative 1 squared is 1, negative 2 squared is 4. It's going to look like this, parabola. But once you get to 0 and beyond 0, you're just going to flatline it to be 0, and it connects right there. So this, trying to bold it so you guys can see this thing. This is the picture of, or the graph of g of x, and it's continuous. But what would f of x times g of x be equal to? When you multiply, because my domains match up, you just multiply the functions. You end up getting 0 times x squared, which clearly is 0 if x is less than or equal to 0, and you get x times 0, which is equal to 0 if x is strictly greater than 0. So either way, you get 0, so the result is the 0 function. So I got two non-zero continuous functions, multiply together is equal to the 0 continuous function. So therefore it is not an integral domain. So the answer to the question that I posed for you, what kind of ring is it? The answer is, it is a commutative ring with identity. So you can think about rings and put things together in terms of sets and define an addition and define a multiplication, and you can get some very interesting looking rings out of it. So, and this is that idea, it doesn't have to be all integers. There's other types of numbering systems out there. You can even look at the concepts of continuous functions and still create the concept of rings. So how many rings are out there? That's always the big question. I mean, or is there a finite amount or is there an infinite amount? Well, we already gave you some examples of rings. So Theorem 3.1 is designed to give you a feel for how big a set of rings that are out there. How many rings are truly out there? So here it is. Theorem 3.1 says this: let R and S be rings. Define an addition and multiplication on the Cartesian product, R cross S. So and I kind of drew this in here. I want you to focus on this. You've got two different kinds of rings here. You've got a ring R and you've got a ring S. So under ring R, you've got a way of adding it in ring R, and you've got a way of multiplying in ring R. And you also have a different kind of ring, S. So there's a way of adding in ring S and a way of multiplying in ring S. So a ring is more than just a set of elements. It's a set of elements with a definition of how to add and how to multiply. And they may not always be the same. So you've got a ring R with a way of adding in R and a way of multiplying in R. You've got a ring S, a way of adding in ring S and multiplying in ring S. Now, this Cartesian product, we're going to look at it as an ordered pair. The first element comes from ring R, and the second element comes from ring S. So this is my notation. Little r comes from big R, and little s comes from big S. So we're going to define an addition and multiplication on this Cartesian product by this. If you got this element, little r comma little s, and you're going to add that to a r prime from ring R and an s prime from ring S. The way you add the Cartesian product, you add components, you add like terms. So you're going to be r plus r prime, but that's inside r, so you add r away. And then you take for the second component on your Cartesian product here, you get s plus s prime, but you're an s in this world, so you add the s way. So you define this addition between the Cartesians is when you get the coordinates. You get the first component, you define it adding it the r way, and second component, you add it the s way. Similarly, under the way we're going to define multiplication is this: r and s multiply by r prime and s prime. Now, you're going to put these guys together to be r times r prime and s times s prime. Okay, so for all r and r prime and r, and s prime and s. Then R cross S is a ring. Now, so with this idea of R cross S is going to be a ring, as we define the paired elements and a way of adding and a way of multiplying. So we have a ring, but there's more to it, because now some of that structure tends to hold over. So if R and S are both commutative rings, they both commute, then so is R cross S. But the only way you're going to get R cross S being a commutative ring is R had to be a commutative ring and S had to be a commutative ring. Okay? If R and S both have an identity, and they have both of them have to have the identity, then so does R cross S. And the identity element would actually be the ordered pair, 1 in R in the first component, and the one element in S in the second component. This is the identity element in R cross S. So what this is really telling us here is that Theorem 3.1, that I've got an infinite amount of rings. Because if I got two rings, I can put them together and create a third ring through the Cartesian product. And this was just pairs. If I had three rings, I could do a Cartesian triple, R, S, and T ring, or whatever the case may be, and do it the same way, and it would create another ring. So you can just keep compounding it and having rings upon rings upon rings upon rings. So there's an infinite amount of rings. But honestly, there's more to the story. Instead of looking outside and trying to grab a bunch of elements and how to figure out how to add some stuff or multiply some stuff, instead of looking outside, you should look inside. Another definition: when a subset S of a ring R is itself a ring under the same addition and multiplication in R. So you got this ring R. You give yourself a ring R. We got lots of them already. Look inside of it and look at subsets. And you look at the same addition and multiplication in ring R. And if this is still going to be a ring, when a subset S of a ring R is itself a ring under the same addition and multiplication, we call that a subring of R. S is a subring of R. You're not just a subring. When you define the word sub, you got to be sub of somebody else. So you kind of have to connect it. S is a subring of R. It's a subset of R that in itself actually is a ring. So let me give you some examples. Now I'm going to use this word subfield, but it's the same idea, because when you got a strong ring, you got all the 11, 12 properties there, you have a field. So for example, the real numbers. You know how to add, you know how to multiply the real numbers. You'll notice that the rational numbers are contained inside the real numbers. And the rational numbers are a field itself. So a field contained inside of another field, that's going to be a subfield. So the rationals, Q, is a subfield. It's a subring, but it's actually a field. Subfield of the real numbers R. The real numbers is a subring. It's actually a subfield of the complex numbers. Complex numbers, A plus BI, where A and B are real numbers. Well, if you make the complex part, the B part, 0, 0 times the square root of -1 is still 0. See, the real numbers are actually contained inside the complex numbers. So the real numbers are going to be a subfield of the complex numbers. But this one I think will hit home a little more. Remember we were talking about the even integers forming a ring, and the integers themselves form a ring. Now the integers is an integral domain. But the even integers are contained inside the integers, and therefore, and the even integers go through the properties, it is a ring inside of a ring. So the even integers is a subring of the integers. Now, look also at this. The integers is an integral domain. It's got all but the inverse, multiplicative inverse property there. It has all the way through that. So it's got no zero divisors and the like. So it's an integral domain. But if you look at the even integers, it doesn't even have the identity, because remember, 1 is an odd integer, not even, so it doesn't have the identity element. The even integers is a commutative ring. So they're not going to be the same kind of ring. The even integers is a commutative ring. The integers themselves is an integral domain, but a ring inside of another ring is called a subring. So if you're looking for rings out there, instead of just trying to grab at the stars and looking at space and trying to group a bunch of things together and defining an addition, defining a multiplication, that's going to be the long way, because then you got to check all 8+ properties to be able to see if that sucker is going to be a ring or not. What you need to do is take the rings that you already know and then start looking inside of them, and I guarantee you're going to find more rings inside of the rings. These are called subrings. They're rings in their own right. They're just contained inside of another ring called a subring. But so for us, what we're going to be doing here is we're going to be proving some things are going to be subrings. So before we do that, and don't forget we got an entire section called 3.2 dedicated to this, but the last theorem in section 3.1 is called Theorem 3.2, and it's basically how you're going to start off to start proving you happen to have a subring inside of a ring. So Theorem 3.2 says this: suppose that R is a ring and that S is a subset of R such that S is closed under addition. Remember, closed means element A and B are elements of S, then A plus B is an element of S. S, the subset, is also closed under multiplication. That means if you have a couple elements, A and B, inside of S, then A times B will also be inside of S. Closure under multiplication. Number 3, the 0 element in R. Now, R is a ring, so it has a 0 element. That same 0 element has to be an element of S. That additive identity has to be inside of S. And it's the same additive identity that was from ring R. And then you got one more property, number 4. If A is an element of S, then the solution to the equation A plus X equals 0 in R is going to be inside of S. That additive inverse, what I need to add A to get back to that 0 element, the additive inverse must also be inside of S. So you got 4 properties. Then S is a subring of R. Now think about it. If I just wanted to prove R is a ring, just to get a basic ring, you got to prove 8 things. It was 8 steps, 8 properties that you have to make a ring. But when you have a subring, it cuts in half. All you got to do is check 4 properties. That's the idea. 4 properties actually make form. When you got a subset that of these 4 properties hold, then that subset actually is a subring of R. We'll look more at this in section 3.2 because we can even combine this down a little bit, but we're going to have to start defining some stuff. And one of the things that we're going to define, because this is very cumbersome, is property number 4. The idea, if A is an element of S, then the solution to A plus X equals 0 in R is an S, the additive inverse. Because what you really want to do is basically subtract A from both sides, and you get 0 minus A, or that negative A. So the next thing we're going to do in our next section, which is section 3.2, is start focusing on identifying and cleaning these type of phrases up. This idea of the negative is going to be defined then, and then we can start cleaning this theorem up to another theorem, theorem 3.4, and it will be a little bit easier, a little less properties to be able to show when you have a subring, and then we're going to use that and prove a bunch of stuff is going to be subrings. So see you on the next video.